So our next talk is John Uhlmann. The title of his talk is up on the screen. GetInjectedThreadEx, Improved Heuristics for Suspicious Thread Creations. Big round of applause for John.
Hello, everyone. So this is actually the third iteration of describing my journey to detect anomalous thread creations. And I read the blurb that I submitted to Kylie last night and realized I've lured a few of you here under false pretenses. So the first version I gave at BSidesCbr in August last year. And at the time, I was using the research topic to teach myself a little bit about PowerShell. And the PowerShell script that I was most familiar with was GetInjectedThread. So I thought, hey, let's learn some PowerShell and let's improve on this existing detection technique. Now, PowerShell is excellent for many, many, many things. This was perhaps not one of them. So the second iteration of this was a technical blog that I did for Elastic Security Labs. And that was the first public release of the script. And in the blurb for this talk, I talked about the script. But when Kylie and Silvio said yes to me coming and talking here, I thought, hey, let's try and do things a little bit better. So I decided to rewrite my thread start address scanner in a little bit of C and C++. So that gave me access to a disassembler, and it literally solved the performance problems, and I didn't even try. And I also discovered a few more things on the way. So if you were looking for a little bit of PowerShell, there will be none unless I failed to update the slides, but there will be C code instead. Quick little who am I? So I'm a security research engineer at Elastic. We're mostly known for our SIEM product, but we do have an endpoint security like a EDR product after we acquired Endgame a few years ago, and then I joined shortly after that. Also a technical blogger for Elastic Security Labs. I kind of put EDR in quotes. I got to write an opinion piece for Elastic at some point. It's about the taxonomy of EDR bypasses, because I think sometimes we're a little loose with what our definition of an EDR is. Anyway, that's talk for another time. So I'm former ACSC, former ASD, about 15 years. Also AWSN supporter, so find me in the Perth chapter room if you want to hit me up on the Slack and want to have a chat. So just a little bit of OS architecture to sort of set the stage for this talk. So a process on Windows, it's a little bit of a lie. It's really not much more than a shared address space. So on its own, it does nothing. It's threads. It's threads that actually do all of the execution. So yes, the first thread in a process, it starts at the entry point in that initial executable. But after that, you should see threads popping up for all kinds of things. They make the developers' lives easier, mostly. They also introduce synchronization and awesome race condition bugs, but that's not today's talk. Basically, users, like if you're looking at what processes are running, there's only tens, maybe hundreds of them. If you're looking at what threads were running, there'd be hundreds or thousands of them. So we don't want to expose all that complexity to our standard users. So we have this concept of processes, which is really just a shared address space. But the TLDR for this talk is that computers run threads. Ergo, malware likes threads. So today's talk is basically scoped. I want to have a look at how malware goes about creating their own threads, because they're just developers and they want to use these nice constructs that makes everyone's lives easier. I want to talk about how we can detect them creating their own threads, and therefore look at about how we can drive that cost into the adversary. So Maddie spoke this morning about burning the in the wild exploits and bug classes. My job is that post-exploitation. I want to burn their in the wild post-exploitation techniques and really drive that cost into the adversary. So GetInjectedThreadEx. So this PowerShell script was released in 2017 at the SANS Threat Hunting Summit. It was a collaboration between Joe Desimone, who's the tech lead working with me at Elastic, and Jared Atkinson, who is over at SpectreOps. And it's pretty much been a little blue team staple for identifying these suspicious threads via their start addresses ever since. So basically, at a high level, what it does is it detects threads that were created with a user start address that is in unbacked executable memory. So unbacked executable memory, it's very normal in processes that do just-in-time compilation, things like .NET that we just talked about, JavaScript engines. There's lots of unbacked executable memory. But it's not that usual for a thread to start in that unbacked executable memory. So usually the JIT engine or the .NET engine itself, it will create the thread on behalf of the JITted code. It's very rare to see the JIT code itself needing to create these threads. Just to put it more visually, up on the screen there, I've got a screenshot of sysinternal's virtual memory map. And it's basically down the bottom of the address space, you see all the purple areas. And that's all of your PE files. That's all your shared libraries. That's your original executable. And that's where you're expecting thread start addresses to be. All that other lovely area up above, all the oranges and the yellows and the light blues, yeah, you can have some JIT code. There can be some legitimate reasons to see some unbacked executable memory in there, depending on the process. But you're really not expecting a thread start address to be pointing ever to that. And that was the crux of that, that initial detection. So how does a bit of Win32 programming, Win32 being Microsoft's sort of lowest level supported API layer, so the create thread API is the thing that you use in Windows to say, hey, I want a new thread because I need to do some good stuff. And it takes two things. One is the address of the entry point of a function, and one is that function has to take exactly one parameter, and so the second thing it takes is the address of that parameter. In other words, it is literally a simple shellcode runner. You can ignore all the other parameters. And it has this lovely sibling function called createRemoteThread, and that is effectively just remote process injection by design. So the original detection was based off the inspection of that start address and just determining whether it's backed by a PE file sitting on disk or not. We want malware to have to be forced to put files on disk because it raises the costs. And if we want to be able to force them to have to put signed files on disk because that raises the cost a little bit further. Now, this particular script, it's a after the fact, a retrospective detection based on saying, hey, kernel, hey, Windows kernel, can you tell me what was the value of the Win32 start address that you stored in your kernel bookkeeping in this structure called the E-thread? Then can you tell me whether or not it's unbacked or not? Now that same information, even though the script is retrospective detection, it is available inline during thread creation notify callbacks that your security product should be listening to. So just on that taxonomy of security products, like all good EDR products, they should be providing you telemetry of suspicious thread creations. And all good EPP prevention products, they should be trying to deny those suspicious thread creations by default, and then only with a mechanism for you to say, hey, actually, no, that's legitimate but somewhat weird software that we bought 20 years ago and is now keeping our whole business alive, to sort of let those ones through. So you will see these legitimate things in the wild. So you will see, for example, a lot of other security products. I won't name names in this talk. I have given other talks where I've named names. And they really should know better. They're a little bit trusting. They think, hey, I'm the only security product here, and they don't have to worry about detecting themselves. But when you've got multiple products, then you're just polluting. Gets a little bit ugly. You will find older copy protection software because it was a newer, it was an emerging area. They didn't really know better. You will find it in a lot of anti-cheat software because they're trying to hide from the cheaters, and that's a lot harder than malware because malware is running on someone else's computer, whereas cheats are running on your computer. So I wouldn't want to be an anti-cheat developer. But it's okay because I don't have to worry about that because no one plays games on their production systems, right? Just stop doing it. I hate the telemetry. Please. And the other major use case I see is Unix software, which has just been shimmed to run on Windows. And Java some of the Java implementations fall in that category. Now, look, I will give them a free pass. Look, JVM, it's platform independent, and Windows is really a second-class Java citizen. It's better to have something that works, even though if it may not work natively, Windows isn't its native target. So, but even with this finite set of exceptions to handle, this detection and/or prevention, depending on whether you're inline in the kernel, it remains highly relevant and successful today. Red teamers, thank you. I love you. So a number of bypasses have been demonstrated and published by the red teamers. Most notably, there's these two excellent blogs. Firstly, Understanding and Invading Get-Injected Thread by Adam Chester, and the second one, Avoiding Get-Injected Thread for Internal Thread Creation by Christopher Pashchen. So there are other bits and pieces around, but I think those two are probably the most seminal pieces. And today we're going to talk through each of the major classes of bypasses and what are the forensic traces that they leave behind, so how we can sort of up our detection game. So just jumping back to the original thread creation heuristic. So it was basically implemented just by a single Win32 API call to ask the kernel, hey, tell me about this thread start, the memory region that belongs to this thread start address. And that information includes this flag that say, hey, you're a PE file, mem image, you're a mapped file, mem mapped, or maybe you're private memory, mem private. Or if something funny is going on, you might be mem free because they've unloaded themselves, and then you've got a dangling pointer and things could go boom, but malware doesn't mind too much about that. Anyway, if it's not image and it's a thread start address, it's suspicious. It was simple, it was quick, and there were deterministic false positives for certain software. So how did malware and red teamers go about bypassing? So in order to do this, so you need a Win32 start address that you can provide to the kernel and say, hey, this is an image back location. But then you also need to very quickly have execution on your shellcode, which is somewhere else in memory. So one way of bypassing this is basically, a thread start address that will very quickly, it will contain some instructions that will transfer execution almost immediately to your unbacked memory. So we call this a trampoline because you're very quickly catapulted somewhere else. So there are 4 broad classes of trampolines. You can build your own from scratch. You can use an illusionary trampoline, or now that we're all talking about Gen I, you can make the kernel hallucinate. Or you can repurpose something else as a trampoline, or you can find a legitimate actual trampoline just sitting there waiting for you to jump on it. This is also known as hooking, spoofing, gadgets, and wrapper functions. And we'll talk about each of those 4 today. Hooking, number 1, bring your own trampoline. So the simplest trampoline is a small hook. You just write the necessary jump instruction somewhere into existing image back memory. These bytes, you could actually even restore them to the original value right after you've done the thread creation. So that helps with avoiding retrospective detection, might help. But recall that your endpoint security product should be doing inline detection on this. So they should be able to see that hooked entry point at execution time, and you need those bytes to actually be there. So here's a little example. Is my favorite function to trampoline by, because debug UI remote break-in in NTDLL, it's actually a legitimate remote thread entry point that you're going to expect when you're debugging software. You just not expecting really to see it on production systems, but a vendor who's like looking at you from 40,000 feet, like they're not going to know if there's not a sysadmin doing some debugging on the live system. That's why you really sometimes need that sysadmin context to really kind of enrich what these alerts are. It's like, hey, is this good or bad? Please, sysadmin, can you click yes or no on your device? Other quick little thing to note is that I used write process memory here because I'm lazy. Most mem image memory is read-only by default. and write process memory actually checks the permissions for you and says, oh, read only, I don't want to fail, I'll make you writable. Then it writes the code in, and then it'll set it back to being the previous page permission afterwards. It's that simple to avoid the detection. Not much at all for the malware author. Luckily, we can detect that a hook start address occurred very easily. So to save memory, Windows ensures that virtual memory for shared libraries, because that's the whole point of having dynamic link libraries, DLLs, the shared libraries, as opposed to having them static and monolithic, is to save memory. Back when memory used to be expensive, it's still good to save memory where you can. But basically, for shared libraries, Windows makes sure that the same backing physical pages are used wherever possible. And they just tag that memory as copy on write. So it's like, hey, it's shared for as long as possible until somebody writes to it, and then we'll give you a private copy, and we'll put a new page into physical memory. So as soon as that hook is inserted, the whole page can no longer be shared. Instead, a copy is created. And even if you unhook later, the fact that a modification had occurred is still lingering around. So what we need to check is, hey, is the start address in the working set, is it in the private memory of that process? Is the accounting saying that memory is against that process, or is it being held against the shared memory in the entire system? Hang on if I jumped. So we can quickly query the kernel memory manager and ask whether or not the page is shared or not. There's an API for that. You can see it up there, query working set EX. So now that we know that something was modified, which is uncommon, but we don't necessarily know whether or not that particular address was hooked. As I mentioned, that could be a false positive because there could be a legitimate hook or some other modification on the image. So in particular, you will find that many security products still like to hook NTDL like it's 2007, and that 64-bit was really a kind of a glimmer in Microsoft's eye. But there is also a plethora of security products out there, of software products out there that just like to extend functionality. So even like the game modding, there's not just game modding communities that we heard about earlier today. There's a lot of people who are like, hey, we know that you don't like to click OK lots, so we've got like we'll mod, so we'll click those text boxes for you because we just want to save you time for clicking things that we know that are going to pop up. There's all kinds of productivity mods that people make to legitimate software. So you kind of got to deal with those as well. And as I mentioned earlier, there's older copy protection stuff like those old packers that like to unpack their code before runtime. So all we really have at the moment is that we know that 4 kilobyte, because that's the default page size on Windows, is private, and then the inline detection would have to then additionally compare, hey, is that, look at a pristine copy of what should be there and say, hey, has it been changed, and then alert based on that. And then once again, to deploy at scale, keep a list of what those rare legitimate use cases are. Number 2, shifting the mat. So I mentioned earlier that security products can do inline prevention at the time of the thread notification callback. So you've got a thread notification callback, and you've got the thread code first running. Are they next to each other, or is there a bit of a window there? So what I said earlier was true, but it's also not quite the whole story. So it's the thread notification callback is called before the thread starts, and it turns out that you can make some modifications to the thread state before the thread is executed. It's not even a race condition. You can, the OS will just let you do it. So in particular, Microsoft does not provide security vendors with a mechanism to determine whether a thread was created suspended or not. So they have a mechanism for saying, hey, you can have a suspended thread, and you can do some stuff to it, and then we'll start it. Oh, but by the way, the callback fired before we let the user do the stuff to it. Because a lot of these callbacks that the security vendors are using, they weren't initially planned for security use cases. So potentially all of the security implications weren't always thought out. And on 64-bit Windows, Microsoft does not let security vendors do our own kernel hooking, so we can't easily check what the parameters were to that create thread callback either. So the malware authors very quickly realized that they could create a suspended thread which triggers the callback, and it looks like it's going into that beautiful purple PE section and the 2 thumbs up from the security vendor. But then they can alter the thread's context. There's a function called setThreadContext, which lets you change the register state. So the registers have like the instruction pointer, as well as all the parameters that will be passed into various functions. Then you can resume the thread. There's also something known as early bird APC, where you can queue a function to run on a thread, and it turns out that those queued APCs actually run before the initial entry point is run as well. So this is basically like you've got this amazing passport control system, and you come up and you show your passport and you check your face, and then after I'm through the gate, I open the unlocked door next to it, and I pass my passport through my mate, and they walk through. It's once again, though, it's not the whole story. Thankfully, effective security products can still do this detection inline. There's a few tricks depending on the OS version that you need to employ, but that's maybe a topic for another talk. Just it can still be done. What about that retrospective detection via our scanning tool? As I said earlier, like you holding up a fake passport, if you're the legitimate person, it works at that point of time, but then if you give it to your mate, like it's not going to hold up to any kind of retrospective detection. So in a normal thread, the user mode start address, it's going to be the 3rd function in the thread's call stack. So when the thread is first allowed to run, the operating system passes down to NTDLL and to a sort of native API, just sort of bootstrapping mechanism, and a function called RTL user thread start runs. And then it calls into the Win32 layer, into this base thread init thunk. And then after that is the Win32, the first user address is called. So when a thread's been hijacked, you're typically either going to see a really odd call stack. So either in that very first frame, suddenly there's no NTDLL and you've got something wrong there, or if you've done the hijack a little bit smarter and you haven't just overwritten the instruction pointer, you've actually overwritten the user mode thread, which is down in another parameter to that in a different register, then you'll see that unbacked address in the 3rd frame. Or for early bird APC, you'll actually see an entirely different call stack. You'll see NTDLL, it'll be in this sort of initialized thunk, and then it's calling NT test alert, which is the way of saying, hey, can you see if there's any APCs pending, and then queue them and run them, and then you'll see NTDLL's user APC dispatcher, and then you'll see the injected code. So you've got this call stack will look really weird if you come back and have a look after the fact. So because I was learning stuff and having a bit of fun, in my original PowerShell implementation, I was like, yeah, why would I want to do the usual, like walking down this call stack? That's a little bit easy. There's functions that do it for you. And on 32-bit, you're pretty much following these saved pointers that point exactly on how big each of the stack frames is. So a stack frame is basically, it's a block of memory related to a function. And then as a function calls another function, there's another block of memory put on top of the stack where it's like all the local parameters and all the data just for that function. And then when it returns, that bit's taken off the top. And when you're coming from top down, it's easy to work out how big that is. So on 64-bit, you look up some exception unwind information, and on 32-bit, you look at these frame pointers and you do that. But I'm like, that's a little bit boring. Let's see if we can climb up the stack with no further information. So with PowerShell, I just did it really rough and ready, and I just ran up that stack as quick as I can. And every aligned potential return address, because it always had to be 64-bit aligned. I wasn't worrying about the WOW64 case. Are you a potential return address? Are you executable? And are you in mem image? And I was getting pretty good results. Sure, sometimes it would mistake what was actually a register for for a return address, for what was a parameter, but I always had the right set of frames, even if sometimes I got a bit confused about the order that they were there. So it kind of worked okay, and I was in PowerShell and wasn't enjoying myself too much, so I figured that was good enough. Came back in C++ and thought, hey, can we do this a little bit better? So I had two things. One, I had a disassembler. No libraries in PowerShell that I'm aware of, but I could now actually look at the bytes that preceded that call site and say, hey, are you actually a valid call site? Was there a call instruction right before where that return address is going to be? So that's an extra data point I had for working out it was legitimate. And then I also had all this lovely unwind information. I could actually say, hey, once I'd climbed up and found a candidate, rather than from the top down where you start, you immediately know what the next one is and you just ask. I climb up, I find a candidate and I say, hey, how big is your call stack? And if that call stack isn't the size of where I am on the stack, then I'm like, oh, nope, you can't be right. So with these two things, I could actually get really valid, perfect call stacks from climbing up from the bottom as opposed to walking down from the top. Alas, sometimes I encountered a dreaded set fpreg unwind opcode. So on 64-bit, in working out what size of the stack is, you have the option on 64-bit to use a frame pointer because sometimes there's a few optimizations that you can make. And as soon as you use a frame pointer, you're now allowed to use a function that should be banned. Alloca lets you allocate dynamic memory on the stack. So you've now got potentially dynamic stack frame sizes. Some people at DEF CON not that long ago used this fact to sort of try and trick stack walkers from basically saying, hey, there's a really big stack frame and it's dynamic, and now just skip over all the bad code. Stack moonwalk, if you want to look that up. Anyway, so if I encounter one of these functions and I'm coming from bottom up, if I'm coming from top down, I can kind of emulate the state and I can know what's the value in that particular register at the time, and I can work out the real thing and I can jump past it. But when I'm coming and I'm cheating and climbing from the bottom up, I didn't have that information. So I really only had a lower bound. But it's good enough, and pretty much this improved sort of stack climbing. It was accurately identifying the initial stack frames in 100% of the very small number of test cases that I ran. So in short, dodgy call stack, you're doing something dodgy, and we can find those spoofed address. Category 3, wrapper functions. So the third bypass is to find a function that does exactly what you want. So there's actually a multitude of these. So for example, the C runtime, which a lot of the Unix folks are familiar with, in Windows, that's written as an extra layer of libraries that sits on top of Win32. And the C runtime, just like the Win32 API, needs to have a thread creation API. Now, in the C runtime, these APIs, the C runtime does a little bit of extra bookkeeping, which is why they wrap the create thread API. And you pass your address into the C runtime, and it then calls create thread with this internal function, and with your thread kind of packed into this little parameter thing. In the case of the C runtime, Microsoft has open sourced the code for that, so you could, if you wanted to, work out exactly where it wants to be, but for all of these wrapper functions, maybe you don't have the code for what's going on. So one thing about these wrapper functions is that without additional tricks, they pretty much can only be used for in-process creations. The exception is load library, and I'll touch on that a little bit later. And those additional tricks, they kind of do exist though. I won't talk about them today, but you should not expect some of these functions like the CRT begin thread. You should not expect to see that in a remote thread creation. Now, when I'm doing the retrospective scanning after the fact and I'm asking, hey, kernel, can you tell me about all these threads and what their entry points are? Now, Windows doesn't do any bookkeeping to tell me whether or not it was created remotely or from a different process or from inside its self-processor. So when I'm scanning, I don't have that context. So it looks very legitimate. But in those inline callbacks that your security products are hopefully using, they are able to make that distinction and they can be more aggressive then in blocking those remote thread creations. Now, on my case, on the retrospective detection front, so we saw earlier that to detect the spoofing, I just had to kind of climb up the stack and find the first 3 frames, and if the third frame, if one of them was private, then we had a spoofing problem. Well, with a wrapping function, I've just got to climb up yet another frame and see if we've hit a private address that early in the call stack. And now, theoretically, yes, this could false positive on some kind of JIT or other legitimate packed code, but I'm yet to encounter a sample of that. All of the JIT engines that I've looked at, they do kind of their calling into their JIT code further down in the call stack. So if I'm just sticking at that first kind of 4 or 5 frames, it's pretty trustworthy that those are going to be towards legitimate P files and not to sort of unbacked JIT memory, which is, so if you do find it, it's probably not JIT at all, it's probably shellcode, which is just JIT by another name and for a different purpose. Yes, I can see a few red teamers out there. Yes, my stack climbing, yes, you can bypass it quite easily by overriding it with some fake data on the stack, particularly since there's a lot of stack randomization, so where you actually start with the stack. Microsoft likes ASLR, address-based randomization, stack randomization. They don't like the exploit writers to know where you are and what your offsets are, so they like to shift you around a little bit. So you could write some false stuff for me to find, but A, I was having fun with stack climbing. Security vendors are probably coming properly. And B, I probably could just save what it looked like in the pristine copy during my initial callback, and then I can later on say, hey, that value has changed. That should never change. Shenanigans are happening here. Or maybe I can just climb a little higher because eventually your shellcode needs to run somewhere. Side note. If any of the red teamers want to play with RTL dispatch APC, I mentioned earlier that there was no perfect remote wrapper function. I thought I'd found it very briefly. So this is used in the internals of APC, where Microsoft doesn't actually queue user APCs. They queue this internal function, which has a pointer to the user APC. And I thought, hey, this should be able to work. But unfortunately, it doesn't check that a parameter is non-null and seems to blow a few things up. But I'm sure there is a way to make it work if people want to play with that. So wrapper functions, we just needed to climb up the stack a little bit further. Gadgets. This is where we get a little bit more interesting, and this is where malware writers started borrowing techniques from exploit writers. So number 4 is in order to repurpose something to do something other than what the original author intended it to do, a gadget. You might have heard of ROP and JOP and all the other things that the exploit writers do to kind of get from this weird state back to stable execution. Well, even when you've got stable execution, sometimes you want to use these little gadgets to trick the OS into doing different things. So our earlier 64-bit hook, it was 12 bytes. And finding an exact 12-byte gadget is fairly unlikely in practice. But thankfully, 64-bit Windows functions use what's known as a fast call calling convention. It's a 4-register fast call calling convention by default. So this means that the first 4 parameters are passed by registers. So when the OS calls our gadget, we have control over the RCX register, which is where the first parameter is going to be. Because if you remember back to the create thread function, we get to say, hey, this is our function, but we also get to specify 1 and exactly 1 parameter. So we've got 2 things that we can deal with. So we can pass a trampoline that is going to sort of jump to RCX and then hide our shellcode final address inside that parameter address. So the simplest 64-bit gadget is then a 2-byte jump RCX instruction, also known as FFE1. 2 bytes, much, much easier to find and basically trivial. In fact, gadgets don't even have to have originally been instructions. They could just be within operands or other data in the code section. So for example, the FFE1 gadget that I found here in NTDL, it was part of the relative address of a GUID. Now, we could come up with a list of all possible RCX to RIP pivot gadgets and try and detect those. Maybe more on that soon. But how about we try and actually detect some unknown gadgets too? Because this technique doesn't actually work yet. So in all modern Windows software, thread start addresses are protected by control flow guard, or CFG. It's an exploit protection. Now, control flow guard has a bitmap of valid indirect call targets that are computed at compile time. So to use this gadget, the malware must typically call set process valid call targets function and ask the kernel, hey, can you just dynamically flip the bit corresponding to that address in the bitmap so that I can use it as a valid indirect call target? This is not a CFG bypass. It is a CFG feature to support legitimate software doing weird things. Now, remember that CFG, it's an exploit protection, so being able to call set process thread calls targets in order to call create thread, like it's a chicken and egg problem. So it's for exploit writers. So it doesn't weaken CFG. Now, like before, to save memory, the CFG bitmap for DLLs is also shared between processes. So this time, to detect whether or not they have modified the CFG bitmap, we just need to say, hey, are you on a shared page, or are you now in the private working set? And if a CFG bitmap page is now in the private working set, and there's a thread start address that corresponds to that page, we probably have a problem. Now, each 2 bits in the CFG bitmap corresponds to 16 addresses. 2 bits is 4 states. So I'm just going to tangent. I needed some sparkly tangent slide here. So Microsoft actually did a pretty awesome optimization with the CFG bitmap. So 2 of those states only correspond to the 16-byte aligned address, whether it's allowed or whether it's export suppressed, which go read about CFG if you want to know what that means. And then there's 2 more states, and they correspond to all 16 addresses, either allowed or denied. So what's with this 16-bit alignment? Well, modern CPUs, they fetch instructions in 16-byte cache lines. So when you're jumping to a function, you've probably moved to an entirely different bit of memory. So when you enter that function, you want as much of the instructions that you're about to execute to be hot in the cache as possible. So compiler writers are like, hey, performance, let's have all of our function entries on 16-byte alignments when we can. So most functions, not all, most functions are going to be on 16-byte aligned addresses. So this means that the CFG bitmap, Microsoft was able to make it 1/8 of the size without any appreciable risk in the increase, or the risk of valid gadgets accidentally being made possible by an overly permissive bitmap. Like a factor of 8 improvement by a little bit of smart understanding of CPUs is pretty awesome. But hang on. So 2 bits corresponds to 16 addresses. So we've got a private 4K page of CFG bitmap. That's 256 kilobytes of code being mapped. Oh, yeah, that's a lot of false positive potential. So all we need to do for our false positives is just hope that legitimate code will, never hope that legitimate code is not going to do that one weird thing. It always does it. So quick shout out here to the WTF bins project. You'll find it on GitHub. It's an attempt to document software that behaves exactly like malware, except somehow it's not. So in the CFG bitmap modification page, I've come across 3 scenarios where it happens. So one is the legacy Edge browser. So they started toggling a few bits after the fact. They tried to unset a few bits to basically make certain abusable functions harder to exploit from their sandbox by making them not valid indirect call targets. User32, it is way too kind to legacy software. Microsoft does this all the time. They are too kind, but they have to be kind. Otherwise, no one would use Windows. So User32, if the developer did it wrong and didn't do this unsuppressing of an export address when they register a callback with User32, then Microsoft will do it for you. So yeah, it should have been compiled in. The developer should have compiled it with the right flags, but Microsoft did it for them and messes a few things up. The other one is security products. So some, most, not mine, security products, they'll drop a page of hook trampolines, and they'll drop it too close to a legitimate module. And as soon as they drop it in there, then they make that CFG code page have to go private. And so that wastes just a few kilobytes of your memory that didn't need to be wasted. Except they'll actually often drop it at a different module's preferred per boot load address. So then in every process, that module needs to be loaded at a non-preferred, non-shared address. So they actually can waste multiple megabytes of your memory, but that's okay. You've all got gigabytes. Right, so we're going to have to deal with false positives because they're going to happen, unfortunately. So like we did before, it was like, hey, let's have a look at what the legitimate bytes should have been, and we can do that comparison. When we're looking for hooks, we'll say, hey, look at the file on disk. Is it what we were expecting? This time it's like, well, once again, the CFG bitmap, it's compiled into the binary and then just kind of mapped into memory. So we could find that in the file of disk. Except it's already in memory. And the copy in that remote process where the thread's being created has been modified. What about the copy in my process? Well, that's clean, and it's there, and it's really quick just to do a little bit of bit arithmetic to say, hey, where in the CFG bitmap in my process is the bits that correspond to that address and have what is the original valid one thing. So all we need to do is find the CFG bitmap. So Microsoft doesn't tell us where it is, but it's a well-known secret that you can easily find the CFG bitmap wherever you want, and there's no point Microsoft not telling us because there's functions that they have to tell us about that have to know where this bitmap is. So you just like look at the first instruction of the function and it's like load address a bitmap, and you just read that address out. So it's really easy to find the CFG bitmap, and you know where it is in your process, and you just find the right offset and read the right entry. Typically you're running in a 64-bit process, so obviously you don't have access to the 64-bit bitmap. If you wanted to do this for WoW64, you just have to compile a 32-bit version and run the detection from there. I haven't implemented that, but feel free, if you're interested, to have a look at that. But anyway, now to detect these gadget trampolines, all we need to do is find the quick offset in our own process, read those 2 bits of memory, and say, hey, is it a valid call target? Because if it's a valid call target, it's probably good, and if it's not, then it's definitely bad. Now, the other approach that I mentioned earlier was to check the purported Win32 start address against a list of known gadget instructions. Alternatively, instead of detecting known bad, can we instead create a model for what good looks like, what a good entry point's going to be? Now, theoretically, 64-bit prologues should really be quite constrained because we need to be able to describe them by the unwind information in our PE file so that we can do that call stack walking and to handle any exceptions and all the other goodness that provides us. In theory, that's great. In practice, there are compiler writers. So it's usually just a couple of pushes of some registers, maybe a stack pointer adjustment for what the fixed size of the stack is, and maybe you're setting a frame pointer because there's a few optimizations that you want to do because you're definitely not calling alloca because that function should be banned. But compiler writers want speed, and so sometimes they add a few extra things into the prologue because maybe, Office is a good example here, maybe they need to be patching a lot. So, and they know that users don't like to reboot, so they had to work out how to do hot patching. So maybe they need to leave a little bit of hot patch space at the beginning of functions such that they can make modifications on the fly. So there's Office. Then there's also jump tables. Sometimes you're not actually an entry point, you're just jumping to where the real entry point is. Or sometimes compilers are like, hey, why set up my whole stack space if the first thing I'm going to do is check to see whether or not the first parameter is null or not, and if it's null, I'm just going to jump back. So leaf functions or stub functions that never call anything else, they don't need to have a stack frame. But any function that is going to call something else needs to have a stack frame. But Developer writers were like, hey, I'm a function, but maybe I can pretend to be a leaf function and never set up my stack frame, and I can just do a quick check to see whether or not the parameter was null or not, and if it's null, I can return before bothering to set up the stack frame. So there's a few optimizations they can do just to save a little bit of time, and all those good savings, they add up in performance. Or sometimes there's optimizations, because sometimes there are wrapper functions. Like there's a function that has, I never actually explained earlier why it's called EX. In the Win32 API, you'll find a lot of functions that have like an EX for extended or a to, or sometimes an EX or a to. It's just Microsoft's way of saying, hey, we wrote the API, we realized it wasn't powerful enough, so we've created a new version and then a new version. So sometimes they use a to, sometimes they use an EX, but it's just a way of saying, hey, here's a new version of a more powerful API, because the first one wasn't quite good enough, but we can't deprecate it because we said we'd support it forever. So sometimes there's a wrapper function, and all it does is it calls the other function, but with a few fixed values. So all it's doing is a really quick set a few things up and then jump to that function. So it's not really a function. Now, in PowerShell, I didn't have a disassembler, so I did this with a really messy regex. It kind of worked, but it kind of was also very fragile and was not that nice to read. In C++, I could write what seems and feels like a more complete Prolog grammar. I won't talk through it today, but it's not actually that many lines of code. In fact, half the lines are commenting about what the code is that I'm trying to write. Like the set of instructions is quite constrained, even when you think about what those additional optimization use cases are. So identifying code that doesn't follow this Prolog conventional is useful, but it could definitely easily be like a rare compiler that I haven't tested against, and I've only kind of tested against the common ones. But like, yeah, Chrome, Git Bash, a few other things that are non-native to Windows, like they won't trigger this particular detection. So as well as the bytes at the entry point having to be legitimate, what about the bytes right before an entry point? So typically, depending on your compiler, this will be a filler byte, because once again, hey, if I want to align my function on a 16-byte boundary, I've got to put something in there. So that filler byte is either usually a 0, sometimes it's a 90, which is the NOP, do nothing instruction. Sometimes it's a CC, which is the int3 or breakpoint instruction. Or sometimes it's actually the end of a proper basic block, so it's either a return or a jump. Once again, though, that's only convention. So like older compilers, they would regularly place like raw data side by side with code, because smashing code and data together never worked out badly for anyone. But that was an allusion to how sort of stack-based overflows work, because you've got your data in your stack as well as your state of execution in the same thing, as opposed to having them separate. And so here we've got what is data, but someone is allowed to treat it as code. But I did some analysis on the Microsoft's compiler toolchain. I pulled down all the binaries on their symbol server. I did this back in 2018. And Microsoft seemed to realize that, hey, if we need to eliminate all these gadget potentials, then we need to really reduce the amount of data that's in the text section is marked as executable. So let's get everything out of the text section that doesn't need to be there. So there was definitely a push in Microsoft at some point, because Visual Studio 2012, it was rife. There was just data everywhere in the text section, marked as executable. It was gadget city. You could always find what you wanted. Visual Studio 2013, it was mostly gone. We're talking small fraction of a percentage that would still do, like sometimes it was like the IAT table would be left there, but most of the data had been pushed out. And then in Visual Studio 2015, update 2, since then I have never seen Microsoft do this. So you still might see false positives with this heuristic, but you shouldn't see it for Microsoft software. You should really only see it for non-Microsoft software that is using non-Microsoft compilers. Or so I thought, until I was updating my slides and I'd rewritten in C++, and suddenly I was getting hits on Microsoft software. I was like, what's going on? So I had a little bit of a closer look, and that data that was sitting there right before that function entry point had some very interesting cross-references. So I'd completely forgotten about extended flow guard, which is another exploit mitigation from Microsoft. So with extended flow guard, before indirect valid call targets, they put an approximately 55-bit hash of what the function and the parameters are going to be before any extended flow targets. And this is harder to bypass than control flow guard for these ones, because you've got to match that hash as well as find the right gadget. So this really increases those protections of indirect call targets. So I'm like, I'm stumped. There's no way I can write a grammar for what is basically a one-way cryptographic hash function, which for all intents and purposes is going to be random. But hang on. Those values were 8 bytes, 64 bits. Why did Microsoft say approximately 55-bit hash? So did a little bit of web searching, did a bit of a look, and I found a nice paper by the folks over at Quark's lab. It's linked up in the slide there. And they noticed that there are 2 masks that are being applied to this hash. One for bits that must always be on, and one for bits that must be always off. They're about 9 bits each. Hence, on average, 55 bits are going to be from the hash, and the other 9 bits are going to be coming from the mask, which is why approximately 55 bits. So hang on, now I had a few bits that I could check. So it's not as perfect, not as nice as it would have been previously, but I can now actually account for those extended flow guard hashes. So a lot of effort here into working out what is valid, what a valid thread entry point is. It's got to be like a function, it's got to be in certain spots, and there's all this different hoo-ha going on. I really would love it if Microsoft just required that thread entry points had to be like named exports, and then maybe they could even just use that name of that export as the name of the thread in the debugger, and everyone's life would be easier because you'd know what's going on in these different states. But it's, yeah, after the fact, trying to work out as best we can. So how else can we detect gadgets? Well, we like to find gadgets in modules that are already there, because if you bring your own module, like if you load your favorite module with your favorite gadget into the process, well, the fact that that library was loaded in the process might be a detection itself. So really, you're going to want to be looking in modules that are already there. Are there thread start addresses in some of these common Win32 modules that you find everywhere? Turns out, as far as I can tell, no. There is a whole lot of Win32 modules that you will find, and I've put up an absolutely definitively non-exhaustive list of modules that should never be a Win32 start address up there. And you can very easily check, hey, are you on this list? And you just make it harder for people to find those wrapper functions, make it harder for them to find those gadgets. As I mentioned earlier, kernel 32 and load library is kind of a little bit of a special case. It's not technically a valid thread entry point, but it's the one that it's spoken about on how to do code injection in like, I think it's Jeffrey Richter's 2005 book on Windows. He's like, this is how you inject code into another process. And that create remote thread where it's load library pointing to a signed file on disk. If you want to inject code into another process and you want to be friendly with the AV product and not get, have crazy amounts of you've been blocked, like do it that way. Inject your code via a signed DLL on disk, and then we can use the signature of that DLL to give the trust to that entry point, as opposed to having to make our best guess with some heuristics. So that is the way that, as security vendors, we'd really love you to do your code injection. Do it that way, and then avoid looking like malware. So the one thing that wasn't in that list, but it's the one library that is absolutely everywhere, is NTDLL. I often put too many Ds or too many Ls in it. It implements the native API, which is the layer between the supported Win32 API and the kernel. So it has to be everywhere in every process. Now, it's absolutely there, so it's the place where I always look first when I'm looking for a gadget. There are actually 4 valid entry points that I've come across. So there is the ubiquitous thread pool worker thread, too many threads in that. there is a thread associated with ETW logging, and then there's 2 threads that are associated with sort of debugging processes. So 2 thread entry points, not threads necessarily. But other than those 4, I haven't come across another valid entry point. So you could very easily say, hey, except for these 4 in NTDLL, everything else is bad, should never be an entry point. And that just raises that bar on finding the wrapper functions, finding the gadgets. Now, in my early PowerShell scripts, I couldn't really rely on having access to symbols, and not all of those are exported. So this was much easier in C++. In PowerShell, I had to go through some really ugly hoops to sort of get threads created in right processes that I could then scan for and then dynamically work it out. But it was much easier doing things in C++, touching the Win32 layer. Turns out I wrote about 1,000 lines of C++ to re-implement this. The original script was 2,000 lines of PowerShell. So it's just, most of that was actually boilerplate on wrapping like all the stuff that was in, like you get for free in C because it's all in the header files. If you're trying to do interop, you've got to like define all these structures and stuff. And particularly when I'm hitting some of the native APIs, they're not always available in PowerShell without crazy effort. So it turns out with gadgets, there are quite a few ways to detect them. So we had was the control flow guard entry, had it been modified? Was there an invalid prologue, invalid tail bytes, or is it from a suspicious module? So sometimes hey, you think you're being neat in bypassing today's detection, but you've actually left this whole big tail. And this is the continual where the blue teams and the red teams help each other, where some blue teamers don't always put on their offensive hat when they're writing something and saying, hey, I've written a detection, okay, now how do I bypass it? And like you have this conversation with yourself and you like work out how you keep bypassing your detection back and forth and improving it until you get to something that's fairly stable. Where do we end up? So the old GetInjectedThread script did not detect any of these 4 classes, as we knew. And the new, well, there is the PowerShell script. It is really slow. I do not recommend it. Or there is the compiled binary, and it is much faster. In fact, most of its time is spent on the first run downloading symbols for just a couple of modules. And then after that, it's really quite fast. And I haven't even bothered trying to make it multi-threaded, which is kind of funny since my whole premise was that more than one thread makes developers' life easier. But we can detect everything that we know of. So don't expect 100% detection from suspicious thread creations alone. You always are going to need defense in depth. In this particular case, typically there'll be like some kind of memory scanning of unbacked memory going on, and also like when unbacked memory is doing suspicious things like calling out to native APIs or to Win32 APIs directly. My whole premise was JIT code should not be calling a Win32 API. Office macros should not be calling Win32 APIs. So if you find unbacked code doing that, that's really suspicious. Or it's some software developer who was trying to work out how to do something weird, and they found a hacker page as opposed to the way to do it that doesn't set off alarm bells. So that said, even though it's not perfect, I still think it's a valuable layer, and just making that a little bit harder. So I'd love to hear about any sort of bypasses that people come up for these thread creations that malware wants to use. So it is actually somewhat easy to hijack a single thread after its creation and run just in that hijacked thread, but sometimes you need to give that thread back to the OS because otherwise, like you might cause deadlock in whatever it was that you exploited, or sometimes you just need more than one thread because that's how the APIs that you're using, or you want to be able to poll out to your C2 at the same time as you're running multiple payloads. Like threads are just nice. And as much as it is easy to hijack a thread and steal it, ensuring that all of your malware's threads, including any third-party payloads or statically linked libraries or reflective DLLs or BOFs or whatever it is that you're borrowing, making sure that they use the exact right detection bypass at the same time for what is the installed security product on that host, that's a maintenance burden for the adversary. So they will make mistakes, and when they make mistakes, we will find their capability and we will burn it. And that's what we want to do. A few references. I didn't put up the couple of blogs that I mentioned earlier, both the original one for GetInjectedThread, and then the two blogs on the classes of bypasses, as well as my early blog on these trampolines, which when I released the PowerShell script, and then the GitHub was updated this morning with a compiled version of my C scanner, for those of you that don't want to install Visual Studio, as well as the source code for those of you who do want to look at the code. I've tried to comment it and explain things as much as I can. And that's it from me.
Thank you very much. We might have time for 1 or 2 questions in the audience. If you can wave your hands vigorously. Do we have any at the back? We've got one at the front over in the middle here.
As long as it's not Pete. He asked his question at C-Sides.
Thank you for that. I was just wondering, do you do this as a after an incident, or do you do this sort of real time during the day, checking for malicious threads and then reporting them where maybe a human could go in and then verify, is this really?
So trying not to talk too much about specific products, but most of the products, like mine, they will, depending on what settings you set, they typically will have a paranoid mode, which is block everything by default. And then you need to come through after the fact, hey, this new software that we bought and installed isn't working, and then we need to add an exception for that, and the sysadmin can do that. Or you can run it in permissive mode, where you let new software run by default, and then the SOC will get the alert saying, hey, there was something suspicious. So mostly it should be running in those thread callbacks, those inline detections. But if you find that your particular EDR product isn't giving you that visibility, absolutely you have the option to run this yourself. I know I see a lot of people with the old PowerShell script, like they set up automation where they would just run it, bring the data back and examine it. There's no reason you can't do something similar if the particular product you have doesn't have that feature. And I know a lot of people in IR engagements also used to use this kind of thing when they're trying to just find out everything that's happening on the system. So, yep. Hopefully that answers your question.
We have a speaker gift for you as well. We'll give it to you backstage. But let's thank John one more time.